designing highly concurrent multi-protocol, multi-tenant services in Scala. So first, who am I? My name is Greg Soltis. I work at Firebase, and the Firebase is a mysterious company. We make a backend as a service, but it's a real-time backend as a service. So what this means is clients connect directly to Firebase. They use it as a database, but when they change values in that database, other connected clients get a callback directly in their client-side code, typically within milliseconds. So our version of Hello World is building a chat application. You can do it in about 5 to 10 lines of JavaScript. And we manage all of this on the back end with Scala. Firebase is an example of a highly concurrent multi-protocol, multi-tenant service written in Scala. That's where I came up with the talk title. All right. So what are we going to talk about? We're going to walk through building a Scala program that understands multiple different protocols. It's going to handle a large number of connections, and this will be for a single server. If you've got a cluster of them, you'll be able to handle many more. And we're going to run multiple independent applications on that one server in that same process. What's so hard about all this? Mostly comes down to managing complexity. We're going to be in a highly concurrent environment, and as we all know, that's a difficult programming environment. So some of the things we're going to discuss are strategies for managing that complexity and keeping it as something we can reason about. Also, dynamically portioning out resources. We're building a multi-tenant server here, and we need to keep applications from interfering with each other despite the fact that they're using shared resources. They're running in the same process. They're using the same access to memory and the network. OK, some quick definitions before we get started. A network protocol. For our purposes, I'm not going to tie it to a specific layer of the stack. We're just going to say anything that requires different code paths to send the same message to different clients. So this could be TCP versus UDP, or it could be responding to a REST request versus sending something out over a WebSocket. The point is we have some code that we can't reuse across different connections. Large number of clients. This number I kind of just picked. It's arbitrary, but the purpose is we want to rule out a single-threaded solution. So kind of with some apology to the Node.js crowd, we are going to handle a large number of clients using threads and coordination between them. Application. This is a little bit of a weird definition for an application. And the reason I picked it is because it approximates a worst case. Most applications, or many applications, you can decompose a bit more than a single thread. Likely all of your applications can be parallelized in some manner. But if we can do this with our worst case here, then your application will be that much more efficient if you can decompose it a little bit. And we'll talk about how to do that as well. All right, so to start with, we're going to handle a single application, just one protocol, and a small number of clients. For a small number, we'll consider this something that we can handle with just a single thread to get started. So for an example, let's say we have some static HTML and JavaScript application being served from somewhere, corporate internet portal or something. We're going to write a web service that'll add a little bit of dynamic content to that. So these are some somewhat contrived requirements here. Given that it's contrived, we're going to pick something that's a little bit overpowered for the job. We use a library called Netty. It is a an asynchronous event-driven network application framework. It's written in Java, but since we're using Scala, we'll have no problem using it. And we use that to manage the networking for our application. So how does Netty work? Netty gives you a couple of different abstractions. The main one is a pipeline of handlers. So each connection they refer to as a channel. Each channel has this pipeline of handlers. Handlers are things that respond to events on that channel. An event might be something like, here's some new data that just arrived on this socket, or here's some new data that needs to be written to this socket, or this channel just closed. And then the pipeline orders these handlers, and you chain them together to get interesting functionality. And we'll see an example of this in a minute. Underlying all of this is the Java NIO library. And Netty manages event loops, one event loop per thread, and assigns channels to an event loop. So what that means is all of the events for a given channel are tied to a given event loop, which is on a single thread. This is one of the ways we'll be able to manage some of the complexity of doing concurrent programming later, is that we'll be able to say, if we're working with this channel, we know it's on this thread. And to start with, we're just going to use a single event loop to keep things simple. All right, configuring Netty. Some of this is going to look a little bit familiar to those of you that have done socket programming before. We're just binding to a host and port. The interesting part is the child handler, where we're saying any accepted connections, use this thing to configure the pipeline for that connection. And this is what the pipeline configuration looks like. So we've got a couple of groups here. On the inbound side, we're saying, OK, this thing is going to take bytes and turn it into an HTTP message or a piece of one. Then we're going to aggregate them until we get a full HTTP message to deal with. On the outbound side, our application is going to produce an HTTP response. And that handler is going to say, OK, I have an HTTP response. I'm going to produce some bytes. And those are going to go out on the wire. And those ones are all standard handlers that ship with Netty. You don't have to use them, but they provide support for a lot of different protocols out of the box. And then the last thing in our pipeline here is our first version of our application, which is going to be a bespoke social, local, big data weather application. We're going to use it to let us know if it's foggy outside the Firebase office and we need to wear a hoodie, or if it's not foggy and we should just bring our hoodie for later. And this is a little snippet of code from that application. So a couple things to notice. We're doing kind of some low-level HTTP stuff here. We're checking the method. We're calling this getBooleanResponse, which is a method that we're going to have to define. Netty is not a full-featured web framework like Rails or Django or something like that. But you can build one on top of it. It provides kind of the next layer down for abstraction. Some other things to notice is we're just directly grabbing our state here, right? So this is going to be a singleton object, and it's just wrapping that Boolean is foggy value. And that's fine, because right now we're on a single event loop, which means we have single-threaded access to this, which means similar to a Node.js application, we're never going to have two requests accessing that at the same time. But for the same reason, it's only going to scale up to a point. Oops. There we go. All right, so what do we have at the end of round one? We can accept gets and posts. We have the Boolean state that we can return and update. As I said, we have no concurrency yet. And our application is directly constructing these HTTP responses. But this means that our coworkers working on the intranet portal can embed a little widget that makes a GET request to our service, and maybe a button that does a post if you want to update it. OK, so our application is pretty successful at this point. Everyone's pretty into it. So we're going to take a couple of big steps here in the next round. The CEO loved it. He wants us to roll it out to the whole company. It's big, multinational. This is going to be a lot of people. Single thread is not going to cut it anymore. And on top of that, our server, let's say a 16-core server, is really pretty lightly loaded. We've got one core busy handling that one thread, but the rest of them are just sitting idle. So we're going to do this by using multiple event loops. In that configuration we saw at the beginning, we were handing off new connections to that event loop that had the pipeline constructed for the channel. This is going to change now. We're going to hand off to one of several event loops chosen by Netty, really round robin, but for our purposes, it's going to look random which channel goes to which event loop. And that's going to give us a whole bunch of different event loops operating concurrently, parsing those HTTP messages or rendering the responses out to bytes. And that's going to solve some of our core utilization issue. We're going to be able to spread the load over our server. Now, quick detour. The marketing department heard about how popular this application was, and they want some stats for a blog post. They want to know exactly how many times that isFoggy value has been read and how many times it's been written. And remembering our definition of an application is that single-threaded state machine, this is going to translate to us having to serialize access to that little piece of state, which means we're going to need some locks, at least to start with here, because now we've got multiple event loops all trying to get that state and update a counter, or update it and update a counter at the same time, and we need to manage that. Okay, the other big step we're going to take in round 2 here is we're going to add some live updating. Refresh is too slow. So we can do this with WebSockets. We'll have the people working on the internet will just open up a WebSocket to our server, and we will be expected to send them the state. And additionally, if somebody changes the state, we'll broadcast that change out to them. So unfortunately, the IT department has a collective motto of never upgrade, and they still use IE6. So we're going to include long polling as well. And this is going to give us our 3 different protocols. In addition, the IT department mandates that everything has to go over port 443, so we can't even cheat and run these protocols on different ports. We're going to have another strategy for dealing with that. But we're lucky. With all 3 of these protocols that we're supporting, which is the basic request response for HTTP, the WebSocket, and the long polling over HTTP, they all start out looking like HTTP requests. And that means when we get that initial header, the initial line for the HTTP request, as well as the headers, we can look at it and figure out which protocol we're dealing with. And this is where Netty really shines, is because that pipeline configuration that we saw earlier is not static. We can reconfigure it on the fly. So we can say, okay, this message that started out kind of looking like a GET request is actually a WebSocket upgrade request. So get rid of all that HTTP stuff we had in our application and swap in the WebSocket handler and let that handle the traffic on this channel from now on. And again, we can do this dynamically. It's independent per channel, even if they're on the same event loop. Oh, yeah. We also need to deal with the persistent connections, right? So we have, before, our application is just request response, right? What is the state, or update the state. Now we've got persistent connections that come in. They want to get that initial value of what the state is, but they also need to register themselves for updates, right? Somebody else is going to change that value. We need to broadcast it out to all the people that are on the WebSocket or long polling connections. All right, so here's a couple of snippets that we're going to add to our application. At the top, you can see the multiple event loops that we're going to use, and this is part of your initial Netty configuration. You can see the change to our pipeline there. So rather than that singleton application that we have, we're going to swap in this protocol chooser that's just going to look at the request and figure out which handler needs to be swapped in later. And you can see an example of that at the bottom, a snippet from the protocol chooser that just says, oh, it looks like this thing is a WebSocket, and I'm cheating here. I'm just using the extension on the URL. But you could look at headers. You could look at whatever piece of the request you want. If you're dealing with something that's not HTTP, you could maybe look at the first few bytes of the request. Or you could just run this on multiple different ports and say, oh, this came in on this port. I'm going to use this protocol. OK. And here's what our application looks like now. One of the things to notice is that there's no longer anything HTTP specific in here. And that's because we have to deal with all these different protocols. But those different protocols don't really matter for the semantics and business logic of our application. So instead, we have our set state, and get the marketing stats, and this new stuff at the bottom that is for the persistent connections to register themselves as needing a broadcast when the state changes, and removing themselves as well, right? So if that WebSocket closes, we don't want to waste time trying to send it or keeping that registration around in memory. And this is what the persistent connections are responsible for doing, is implementing this trait. And what this allows the application to do is just say, OK, there was a state change. I'm going to loop through all these registrations I have and broadcast that state change without needing to know what the underlying protocol is, right? So our application no longer needs to know about WebSockets or long polling or anything like that. We just need handlers that implement that trait. And this is the top piece of the WebSocket handler here, right? So this is our definition of different protocols. The WebSocket framing is going to look different from the response to a long polling request. OK. So here we have the end of round 2. We have capacity for a large number of clients. Like in this example, I'm using 32 event loops. You will be able to get that 100,000 number with that many event loops. We have a protocol-independent application interface, right? So this is some pretty good design. We no longer have HTTP semantics inside our application code. And similarly, the protocol-independent broadcast interface is also good design. The application doesn't need to know anything about how that broadcast happens. It just performs it. And we have a mix of protocols. We have some that are request response and some that are subscription for broadcast. And so I have all the code for this up on GitHub, and the link will be posted at the end. If you go and look at it, we also have a lock around the state. Anytime you're doing an update or a read, you're going to have to grab that lock so we can do the proper marketing stats and fulfill the definition of application that we talked about in the beginning. All right. So now we're going to make this multi-tenant. The app has gone really well, and one of the other engineers noticed that we could take this idea of just synchronizing Boolean values and apply it to a bunch of problems. The Boston office wants to know if there's a baseball game. New York City office wants to know if Uber is currently banned in New York City. And maybe HR loves it so much they want to apply it to their PDF to Word resume converter for some reason. But the problem, the accounting department doesn't want to pay for another cluster for each of these applications. And they're observing that the latency is a little spiky on the machine that we have, and the cores are still a little bit underutilized. It's a very technically savvy accounting department. OK, so we've got our generic interface for separating out the protocols already. We did that in the last round. But now we're going to need a generic application interface for just synchronizing Boolean state. We're going to need a place to define the application parameters, right? So some of these applications might have subtle tweaks or behave a little bit differently. So just some way to manage that complexity. And finally, a way to manage the concurrency for each of these applications. So to do define the application parameters, you don't have to do it this way, and in my example code, I just kind of hard-coded them in. But the way to do this is to have some sort of external queryable data store and have a mapping for some indicator in your protocol to which application to run. And especially if your multi-tenant applications, like in this example, exhibit more or less the same business logic. Like for this one, we're just synchronizing Booleans for all of them. They just have they're separate Booleans. They mean different things. And for us, since we're using HTTP as kind of like the initial bit, we can do a URL to application mapping. So you could keep that in some key value store or file system or something like that. But in general, it's good to keep that outside the process so you can update it without having to restart the process, which will kill all those persistent connections. So this will let you, deploy the is Uber banned in New York City without disrupting the is it foggy in Soma. Okay. Managing the concurrency is going to be a little bit tougher for this, right? So previously we had just that one lock around the state, and that was kind of okay. We had safety. We would occasionally get things maybe backed up, waiting on that lock. But that's not really going to work for this multi-tenant application. Blocking on that lock blocks the underlying Netty event loop. Which previously was kind of okay because all of the traffic was going to the same application. If that application was slow, kind of expect all the traffic for that application to be slow. But now we have multiple applications. We said part of running a multi-tenant service is to keep applications from interfering with each other. And so these two things kind of conspire to give us a problem, which is that blocking one of these event loops is blocking kind of a random subsection of traffic for other applications. And if you have one pathological application that's really slow, it's pretty easy to quickly block all of your event loops. So this simple locking strategy is not really going to work for us anymore. Instead, we're going to use Akka. Akka is an actor library. Actors are very lightweight concurrent entities. They process messages asynchronously using an event-driven receive loop. Sounds kind of similar to the Netty description, but we'll get into some of the differences in a second. Just quickly discuss actor systems. An actor is a behavior function and a mailbox that is typically a queue. And that queue contains the messages to process for that actor. The actor system is responsible for successively calling that behavior function with each individual message from the mailbox. And typically you can multiplex many more actors than threads over a single thread pool. So we might have 1,000 of these applications running on like 32 threads or something like that. And one of the guarantees that we get from the actor system is that a given actor is only processing a single message at a time. So they behave in a single-threaded fashion, even though the actual thread that they're running on might change from message to message. But that's fine for us. All we need to know is that we're serializing access to our application state. We don't actually care which thread it's on. So the quick comparison here between Akka and Netty. First of all, they both could be used by themselves to solve this problem. However, they have kind of their own separate strengths, can make it a pretty good idea to combine them. So Netty is extremely tuned for network performance. They've really put a lot of time into minimizing allocations and tune properly, and you can minimize copies in your pipeline. and you have that nice kind of single-threaded access to your channel. It's always on the same thread, so you can use thread locals if you have some state associated with it. Whereas Akka is a bit more generic. You're never guaranteed which thread your code will be running on, only that it's only going to be running on one thread at a time. But it's also a lot more dynamic. You can decide, like, okay, I've got this stream of events coming into one actor, and I want to filter out some of them and send it to this other actor. And you get to manage your concurrency in kind of more interesting ways that way. With Netty, you can do that. It's a little bit more difficult, though, to move event streams from like one event loop to another one and to reorganize them according to properties of the messages rather than which channel they came from. Okay, so let's talk about actually using these actors in our application. So the goal here is to not block Netty's event loops, right? Because we don't want to block that random subsection of our traffic. So what we're going to do is when we decode some message off the wire, maybe it's a get, right? We want to know what the current state is. We're going to send a message into the actor. We're going to enqueue a message in the mailbox. We're going to use what's called the ask pattern that is part of Akka. And what that really just means is we're going to enqueue this message. It's going to return a future. And when the actor responds to that message, that future will be completed. And then we can continue on from there. And it's the same bit for actually changing the state. We're going to send in a message with the new updated state that we want to set. And we're going to wait for that future that is going to say, OK, the state was changed. You can respond to the client now. One other interesting piece is that, remember, we have to register those persistent connections. If they want to get broadcast events whenever that state changes, we need some way for our actor to do that. So those registration events are also messages that we send into the actor. There's a couple of ways to handle this. You can send in some object that knows how to get back into the Netty event loop. You can perhaps wrap your clients in other actors, and then the actor that you're using for your application can just send a message to them. There are sort of trade-offs to both of those. One of them is managing context switching, actually, depending on, since you're not guaranteed what thread the actor is going to run on, you may want to guarantee that it's going to go right to the Netty threads. All right, so this is what the messages that we're going to send to our application look like. Scala really helps us out here with guaranteeing that these are going to be immutable, as well as we're using a sealed trait. So that means our actor can say, given that we've got one of these Boolean sync app messages, we can write a match statement that will have is guaranteed to handle any one of those messages that we could get. There's a little bit of weirdness with type safety in Akka, but once we have one of these, we can do an exhaustive match. And this is what the internal bit of the actor looks like. So here we're saying, OK, we've got one of these Boolean sync app messages. Which one is it? All right, it's a get. We're going to handle that. And that last line there is sending the state back. And that's going to complete the future. And that's going to let the code that sent that message in, it's going to get the onComplete for the future, and it can go right back into the Netty pipeline and send that response. One thing that we don't have in here is locks around the state. So we're guaranteed by the actor system that this thing is only processing one message at a time. So as long as it encapsulates our state, it's giving us that serializability that we wanted for our application. All right, so this is what our server looks like at the end here. We've got multiple protocols, the request response or persistent broadcast. We have a whole bunch of Netty event loops so that we can handle all of that traffic. And then we have the actor system so that we're not blocking the event loop when we are interacting with our application. If we have that sort of pathological slow application, that mailbox is going to grow, but other applications will continue to be able to handle traffic. And a couple of extra results that were not initial goals, but turned out to be pretty nice. We have that interface for new protocols, right? They have to send those messages and just implement that trait if they want broadcasts. So that's pretty easy. If you have some new, you want to add just a raw TCP socket to this program, you can do that. We have the protocol agnostic interface for each application, right? Our application just deals in those messages that we saw. You're just sending them and waiting for the futures, which makes things easier to test. Testing your application logic no longer requires anything involved with any of the networking. You don't need any of the WebSockets. You can do it all synchronously and local, which is great for business logic tests. And finally, because that actor is guaranteed to only be processing one message at a time, that log of all the messages that we process is an effective audit log for our application. If something goes wrong, there's some bug in our logic, and we have that log recorded somewhere, you can go back and play it over and step through all the different state changes and see where things went wrong. And as long as you have that log, you can do it over and over, and it's guaranteed to be the state changes that your application went through. And in addition, that actor, one thing I forgot to mention with the actor system is this is a good place that if your application is decomposes a bit more than just the single-threaded state machine, this is a good place to do it. You could have a bunch of child worker actors that you could fan work out to, or whatever hierarchy you want. That's kind of the nice thing about being able to filter out some events and send maybe some of them to one actor and some of them to another actor. You really get to choose based on the semantics of your application rather than what socket that event came from. And that's it. So this is the GitHub link there has the code for the application that I wrote that I stole the snippets from. You can find me on Twitter, and if you're interested in this kind of stuff, Firebase is always hiring. We have time for questions? Yeah.
I'll just ask you to repeat the question.
Oh, sure, yeah.
Do you run your actors across the network on different machines, different processes? And if you do, what do you do with the at most once delivery guarantee?
All right, so the question is if we run our actors across different machines and how do we deal with most once guarantee. So we actually don't, although you can. You're gonna have, anytime you're gonna queue up some, essentially a job queue at that point, you're gonna be dealing with that problem. The best I can offer is try to make your operations idempotent, so if they get, if they're received multiple times, it's okay. But fundamentally, you're gonna have to choose between at most once or at least once. Yeah. Yeah. So how do we handle that Akka does not guarantee delivery of the message? So we have our Akka actor system is contained locally. So it's not technically guaranteed, but the set of things that can go wrong in that case tend to be catastrophic things like the JVM crashed, rather than more typical failures like the network connection flapped or something like that. Also, we have we've done a bit of logging with the dead letter mailbox. So if you send a message to an actor and that actor no longer exists for whatever reason, it gets sent to this special mailbox called the dead letter mailbox, and we log those and look for them. Yeah.
Can you speak to why you chose Netty Java-based versus Spray.io?
Let's see. So the question was why we chose Netty versus Spray. So I can't speak too much to it because it was before I got here, but it's the Netty folks have been great in terms of what they're working on has tended to align very well with what we're working on. They're really just focused on performance. They've done some kind of interesting tricks, especially for something on the JVM. Like they have reference counting for their buffers, which is weird in a garbage collected language, but they're actually doing things like that for good reason. So we've been pretty happy with it. Netty's never really been a bottleneck for us. I don't really have much experience with Spray, so yeah.
So in real life, do you expose Java solution directly to the web, or do you proxy it with something like
Sorry. In real life, do we expose the Java process directly to the web, or do we proxy it? So we expose it directly to the web, although we have a bunch of other stuff in there to kind of manage some of the common problems you can have with doing that. In particular, SSL. Netty recently released an update where they forked a small piece of Tomcat's native module, and you can use OpenSSL from the JVM, which is pretty nice because it's much, much faster than the standard JVM SSL. All right.